Hey, welcome back. This is section 10.5 on ionization constants for acids and bases. So the goals for this section are we want you to be able to write the ionization constant expression for a weak acid. And the ionization constant we abbreviated as Ka for a weak acid. And we want you to be able to write the ionization constant expression for a weak base. And ionization constant for a weak base is abbreviated Kb. We'd like you to be able to know and describe the relationships between acid strength, percent ionization, and Ka value for a given weak acid, and then use the Ka value, the ionization constant for a weak acid, or the percent ionization to calculate the concentration or amount of weak acid HA, conjugate base A-, and protons or H3O+ hydronium ion in a weak acid solution. So the ionization constant for a weak acid or a weak base, Ka or Kb, is similar to the equilibrium constant we talked about back in chapter 9. Keq was the concentration of each of the products raised to their coefficient multiplied together, divided by the concentration of each of the reactants raised to their coefficient multiplied together. So this was Keq. Ka for a weak acid, or Kb for a weak base, is very similar if you can check it out here. The only difference is we don't use the coefficients when writing the ionization constant for a weak acid or a weak base. So the ionization constant for a weak acid is the concentration of each of the products in the acid-base reaction multiplied together, divided by the concentration of each of the reactants multiplied together. So the Ka for weak acids, or the Kb value for weak bases, shows the strength of the acid or the bases by quantifying essentially how far to the left or to the right the reaction is pushed, whether the weak acid or weak base reaction favors the reactants or the products. Just like with equilibrium reactions in Keq, the value of Keq, whether it was about 1, significantly greater than 1, or significantly less than 1, gave us an indication of if the equilibrium reaction favored products or reactants and by how much. Same thing with Ka and Kb. When we calculate Ka or Kb, if you have a Ka value that's significantly greater than 1, it means that you have a high concentration of products and a relatively low concentration of reactants. So if your Ka value is significantly over 1, a large Ka, that means that when your acid HA plus H2O, our general weak acid expression, makes H3O plus A-. If Ka is large, meaning you have a high concentration of products, that means that almost all of your acid had to ionize to make H plus A-. And then of course the H plus was accepted by water, which was acting like the base, and then we made the conjugate base A-. So large Ka values, significantly greater than 1, mean that you have stronger acids that ionize more completely. If you have a Ka value that's low, that's less than 1, it means that your concentration of products is relatively low and your concentration of reactants is relatively high. So in our expression, HA, our equation, plus H2O is in equilibrium with H3O plus A-. If you have a relatively low concentration of products, it means you didn't make very much H3O plus or A-, which meant that you had a low ionization or an incomplete ionization of your acid. It didn't make H plus very much. Therefore, there wasn't very much H plus to protonate the water to make hydronium ion and to generate the conjugate base A-. So low Ka values or Kb values give us an indication that we have a weak acid or a weak base. So if your Ka or Kb value is greater than 1, is large, that means the equilibrium position for the acid-base reaction, HA plus H2O, is in equilibrium with H3O plus A-. That means your equilibrium position favors the products. Right, it's being pushed towards products. All of your acid is ionizing. to generate protons, water is accepting the protons, and you're making a lot of product. So if you have large Ka or large Kb values, you have strong acids. Because strong acids by definition, or strong bases, if we're talking about Kb, they ionize completely or they accept all the protons in solution. If you have a Ka value or a Kb value that's about 1, you have about equal products and reactants. The reaction isn't favoring one direction significantly over the other direction, like products over reactants or reactants more than products. This is unusual in acid-base reactions because usually we have either strong acids or a weak acid. It's unusual to have something that's like close to 1. Usually your Ka and Kbs are either significantly greater than 1 or significantly less than 1. And then if your Ka or Kb value is less than 1, just write out this reaction again. This is one you want to know how to be able to write. H3O plus A minus. If your Ka value is small, that means that the concentration of reactants is relatively high and your concentration of products is low. So your reaction favors the reactant side or is pushed to the left, which tells you that not much of your acid is ionizing. If you're not producing much H plus A minus due to the ionization of the acid, that means you're not able to make much product. So weak acids have relatively small Ka or Kb values. And again, Ka is for acids, A for acid, and Kb is for bases, B for base. So this is how you write the acid ionization constant, the Ka expression, for your general acid-base reaction where you have any acid, Ha, reacting with water to generate hydronium ion and the conjugate base A minus. The Ka value or expression is the concentration of each of your products multiplied together, divided by the concentration of each of your reactants multiplied together. So in this case, our products are always going to be H3O plus. And then the conjugate base of our acid, A minus. And then our reactants, we exclude pure liquids, solids or gases. So we don't include liquid water. So we just have Ha on the bottom here. For the Kb expression, it's the reaction of a base with water. If the expression is written the same way, you have the concentration of each of your products multiplied together, divided by the concentration of each of your reactants multiplied together. And remember, with Ka and Kb expressions, you don't include the coefficients in the balanced equation. It's just the concentrations. And that's how this differs from the Keq expression where you have to include those coefficients. In Ka and Kb expressions, you don't have to include the coefficients. It's just the concentrations of each product multiplied together, divided by the concentration of each reactant multiplied together. Okay, so in a base reaction, you have your base. It's accepting a proton from water. And depending on if it's a strong or a weak base, a strong base is going to accept all of the protons it can from water. And so the reaction will be pushed towards products. And if it's a weak base, it's not going to accept very many protons from water. So the reaction is going to favor the reactant side for a weak base. So to calculate the ionization constant, the base ionization constant, you take the concentration of each of your products, the conjugate acid of the base, BH plus, and the conjugate base of water, OH minus, divided by the concentration of your reactants. And again, we don't include water because it's a pure liquid, so it's just the concentration of your original base. So acid strength can be expressed also by percent ionization. So we know that with a higher Ka value, a larger Ka value, that means we have a stronger acid because more of the acid is ionizing, so more products are being produced. So if more acid ionizes in water, the percent ionization is going to be higher. Like if for strong acids, we know our percent ionization is about 100%. For weak acids, it's usually less than 5%. So this tells us how much of the original acid turns into ions, the H plus ion plus whatever the other negatively charged ion is. So for example, let's say we have a weak acid and we say it's 2% ionized in solution. That means if the acid concentration is 10 molar, then the amount of the acid that's ionized is 2% of 10 molar. So 2% of 10 molar is 0.2 molar. So what this means is that in our reaction, HA plus H2O, H3O plus A minus. If we start out with 10 molar weak acid and 2% of it is ionized, that means 2% of 10 molar turns into these ions, because 2% of 10 molar turns into H plus A minus. And each time we make an H plus and an A minus, we're able to make 1 mole of each of our products. So if 2% of 10 molar is ionized, that means 2% of 10 molar turns into each of our products. So each of our product concentrations is going to be 0.20 molar. 10% of 10, or sorry, 2% of 10 molar, because the weak acid is 2% ionized. That means that at the end of the reaction, once 2% of 10 molar has been ionized, at the end, all we have left of our original weak acid that we started with is the original 10 molar minus the amount that was ionized. So we started out with 10 molar minus 0.20 molar was ionized. Gives us 9.8 molar left. And so it's these amounts that are present once the reaction has reached equilibrium, which I'm putting in orange boxes, that you would plug into the Ka expression. So we can go from a percent ionization and a starting concentration. We can calculate the concentration of each product generated based on 2% of the original acid being ionized. And then we can calculate the concentration of the weak acid that's left once the reaction has reached equilibrium. And it's these values that you then plug into the Ka expression. Ka for this acid is the concentration of the product. So it'd be the concentration of H3O plus 0.20 molar times the concentration of the other product, A minus, so times 0.20 molar, divided by the concentration of the reactants, multiplied by each other. And we don't include water because water is a pure liquid. So our only reactant is the 9.8 molar weak acid that's left after 2% of it is ionized. So times 9.8 molar. And you would multiply the top two together and then divide by the bottom, and that would give you your Ka value. So we're going to do a sample problem to calculate Ka from percent ionization to show how this all works all together. But just keep in mind that the more acid that's ionized, the higher your Ka value will be, meaning the stronger acid that you have. Okay, so here's our percent ionization example problem. So you have a 0.0100 molar solution of acid HA that's 15% ionized in water. Calculate the acid ionization constant Ka for this acid. So I outlined some steps. The first thing you want to do is you want to write the molecular equation for the acid reaction in aqueous solution. So you want to write that you have HA plus H2O, it's an aqueous solution, is in equilibrium with H3O plus A minus. Let me just get rid of that so we can actually see. Then from the problem statement, we know that the concentration of H3O plus, let's write this reaction up above so we can keep it in mind. HA plus H2O, H3O plus A minus. So from the problem statement, we know that the concentration of H3O plus is going to be 15% of the concentration of HA because it's 15% ionized. So if HA is 0.0100 molar, that means H3O plus is going to be 15% of that. It means that A minus is also going to be 15% of that because each time HA ionizes to form H plus and A minus, the H plus forms 1 mole of H3O plus, and it forms 1 mole of A minus. So the concentrations of H3O plus and A minus are going to be equal. So once we calculate 15% of our starting acid concentration, we know these two concentrations, H3O plus and A minus. And then to figure out the concentration of HA, once equilibrium has been reached, once it's ionized as much as it's going to, you take the starting concentration minus the 15% that was ionized to get your final concentration. So let's do this on a whiteboard together to kind of walk through these steps. Okay, so here's our problem statement. We have 0.0100 molar solution of an acid is 15% ionized. Let's calculate the Ka. So you write your equation, HA plus H2O goes to H3O plus A minus. So we start out with 0.0100 molar. Doesn't matter how much water we have at the beginning because it's a pure substance, it's a pure liquid. And we don't have any of these. And then it's 15% ionized. So we're going to gain whatever 15% of this is on the product side, and we're going to lose 15% of the starting value on the reactant side. So plus 0.0100 molar times 0.15. And that's a negative because we're going to be losing that from the reactant side, 15% of 0.0100 molar. And on the product side, we're going to gain 0.0100 molar times 0.15. And here we're going to gain the same thing, 0.0100 molar times 0.15, 15%. And so our final concentrations, when you add each of these, 0.0100 minus, because you're losing this amount of the product, of the reactant, minus will give you the final amount of HA. And then when we add these amounts here, it'll give us the final amount of each product. So let me plug this into my calculator. So 15% of 0.0100 molar is 0.0667 molar. And so 15% of 0.01 molar, 0.0667 molar. And same thing here. So now when we add these up, we get 0.01 minus this amount, because this is the amount that's being lost from the reactant. The reactant is losing this amount of concentration as it's converted into product. So our final amount of weak acid is 0.01 minus 0.0667. And all of my numbers here are off by a decimal point. So let's just adjust that. Make sure you do your percent calculation correctly. So 0.01 times point. So I just had a major calculator error. So 15% of 0.01, let's just redo that calculation here as I realize what the mistake was. 15% of 0.01 is 0.0015. 0.0015, 0.0015. There we go. And let's just show how I got that up here. Okay, so that's how I got that. So for the reactant, that's the amount of reactant that's consumed in the chemical reaction. 15% of it is ionized. So 15% of the weak acid turns into a proton in the conjugate base, meaning 15% is converted into these two products. So we have to subtract that from the original concentration because it's no longer there once it's been used up in the chemical reaction. So for my final weak acid concentration, I get 0.01 minus 0.0015, 0.0085 molar. And for my concentration of conjugate acid formed at once the reaction has reached equilibrium, it's 0.0015. You add those two, and same thing here. You started with 0, and then you produced this much. So 0.0015 molar. So now we have everything we need to plug into the Ka expression. Ka equals the concentration of H3O plus times the concentration of A minus. Each of our products multiplied together divided by the concentration of our reactant, HA. And we don't include water in the denominator here because water is a pure liquid, so it's not included in these K expressions for acid or base ionization constants or the equilibrium constant. So let's plug in our values. We have 0.0015 times 0.0015 divided by 0.0085 will give us Ka. And I get equals, scientific notation, 2.65 times 10 to the negative fourth. And I want to check my sig figs. So I had out to the thousands place here. So out to the 10,000s place. So to there, out to 4 decimals, all of these out to 4 from these addition and subtraction steps. So that gives me 2 sig figs on each of these when we get to the multiplication and division step. So I should have 2 sig figs in my final answer. So equals 2.7 times 10 to the negative 4. This value is significantly less than 1. If we wrote it out in decimal format, 0.00027. So it's less than 1. So the Ka shows us that this is a weak acid. It doesn't ionize very much, only 15%. Okay, so that's how you calculate Ka, given the percent ionization and the concentration of the original acid. So I wrote out all the steps on the PowerPoint slides too, so you could follow along with how I wrote it out, and you can also check it out on the slides. Start by writing the equation for the reaction, and then calculate the molar concentrations of each species in the reaction that you're going to be plugging into the Ka expression. So your concentration of H3O plus is 15% of the starting concentration of your acid. Your concentration of the conjugate base, A minus, is going to equal the concentration of hydronium ion, because each time one hydronium ion is made, you're also making 1 mole of conjugate base. So those two have equal concentrations. And then the amount of the weak acid that wasn't ionized, that's present in the solution once it reaches equilibrium, is the starting amount minus the amount that was ionized away. So you take the starting amount minus the amount that was ionized to give you your final amount. Once you have all these concentrations, you plug them into the Ka expression, analyze on your calculator, and then you end up rounding to 2 sig figs. Okay, so if you were interested, I posted a Kahoot quiz online. It's a practice quiz number 1, I call it. There's going to be practice quiz number 2 at the end of the next section of lectures. But practice quiz number 1 covers what we've done in chapter 10 so far up to the end of section 10.5. You can play it by clicking on this link here, and then you enter the Kahoot ID that's below in bold. The quiz is optional. You can just play it to get extra practice. It's something that I would normally do, live in person as a fun activity to help everybody review. And I found a way we can still do it online, even if we're not doing it all at the same time. So let's try this out. Let's see how it works. I hope it's fun. I hope it helps you study for the quiz, so that the quick quiz at the end of this week, you can get a really high score on. Okay, let me know if you have any questions, and hope you have a good day. Bye.